First of all, you now know about parametric timed automata, but sometimes you need parametric probabilities in order to capture imprecisions, robustness, and dimensioning issues. So let us now introduce parametric interval Markov chains. Markov chains are like this example, where basically it looks like an automaton where you have different locations. So here you have an example of an automaton with starting in location 0 and with three other locations 1, 2, and 3. And in between two locations you have the transitions with a probability on it. So if you look at state location 0, you can exit it with a probability 0.3 to go to location 2 and a probability 0.7 to go to location 1 here, etc. So what you notice here is that to exit a location you have some probabilities, and these probabilities, these exiting probabilities, they add up to 1. 0.7 plus 0.3 equals 1. And that reflects the fact that the probability of exiting a state, well, eventually by looping on itself, is always 1. You capture all possible executions. So this was a Markov chain. Sometimes we don't know the exact values of probabilities. So for example, we don't know that here it's 0.7 and here it's 0.3. We just know that they add up to 1. So in this case, maybe we want to capture several probability values within an interval. And so an interval Markov chain, as on the right-hand side of this slide, is similar to the Markov chain we have just seen, but on the transitions, instead of having an actual value of a probability, you have an interval. The interval has a lower bound, for example 0.3 here, and an upper bound, for example 0.5 here. These intervals allow for specifying that the probability should be between the lower bound and the upper bound. So we don't know in this case whether the probability is 0.3, 0.4 or 0.5 or whatever in the interval. We just know it's inside the interval. You can see that this interval Markov chain on the right hand side of the slide is a specification which allows for the original Markov chain to be an implementation. Okay. And this is actually the case, as you can see there. There is the similar structure. In fact, you can see that the probabilities are included in the intervals for all probabilities. Moreover, the implementation satisfies that the sum of exiting values from a location is always 1. So this is the case for exiting 0, it is also the case for exiting location 1, etc. Okay. So we say that an interval Markov chain is consistent if it admits at least one implementation, which is the case here. Now we want to add parameters, because sometimes we don't know about the upper or lower bounds of these intervals. So we will introduce in the bounds of the intervals parameters. Here you have an example where we have two parameters, a parameter P and a parameter Q. As you can notice, parameter P occurs at several places, here and here as well, while parameter Q also occurs at several places. That means that for exiting location 1, you can use the subloop with a probability that is between Q and 1, or exit to go to location 3 with a probability that is between 0.3 and the same Q. So in order to obtain a corresponding interval Markov chain, it is enough to evaluate the parameters here, in this example P and Q, with a valuation, and it gives an interval Markov chain without parameters. A key property for interval Markov chain is consistency. Consistency is defined in an inductive way. So we first say that a state S in an interval Markov chain is zero consistent if there exists a probability distribution over its successors that matches the intervals. So we just look at the outgoing arcs of the location of the state, and we check that we can find a probability distribution so that it sums up to 1. Then we say that a state S is n consistent with n greater or equal to 1 if there exists a probability distribution over the successor of S that matches the interval, so it's similar to zero consistency, but also that the successors of S prime, that are considered in this distribution, so that we can obtain by firing a transition with a strictly positive probability, are n-1 consistent. So if I'm in a state S, I can go to a state S prime with a probability rho of S prime that is positive, strictly positive, and this S prime must be n-1 consistent. An interval Markov chain with n state is consistent if its initial state is n consistent. So let's take a first example. This example is the same as the one we had before, and we can notice that for all states from 0, 1, 2, and 3, all these states are zero consistent. Indeed, for each of them, I can find a probability within the exiting X intervals such that the sum adds up to 1. So, for example, if I consider this state 1, here I have to choose a probability between 0.5 and 1, and here a probability between 0.3 and 0.5, such that the sum is equal to 1. So if I choose 0.5 for each of them, that is fine. And I can do the same thing for all these states. Okay. But for state 4, let us look at what happens for state 4. State 4 is such that there is a probability 0.6 of exiting state 4 to go to state 3, and there is a probability that must be between 0.5 and 1 to loop on state 4. Meaning that if I want a sum that is 1, because of these 0.6, I need to have 0.4 on the other arrow here. But 0.4 is not in this interval. Therefore, state 4 is not zero consistent, and we have marked it here. So all states in this example are zero consistent, except state 4 that is not. Now let's look at one consistency. If we consider state 2, which is the most interesting here. So state 2 must have, to be one consistent, must have a distribution rho such that the sum of probabilities adds up to 1, but also that all states that are reachable from 2 are zero consistent. We know that state 4 is not zero consistent. So we should not go from state 2 to state 4. Therefore, we must choose a probability 0 to go from state 2 to state 4. This is possible since 0 is included in the interval. Now, if I have 0 for this interval, can I choose a probability in the remaining intervals here and there so that the sum is 1? Yes, I can take 0.5 in both intervals. So state 2 is one consistent. I can check also all the other states and see that they are all one consistent. And if I repeat the procedure, I will notice that all states are n consistent, whatever the value of s, except state 4 that is not even zero consistent. Let us now address the second example, which is a little different. So here we have a state 0 with two transitions exiting state 0, a self loop with a probability 0.51, and a transition going to state 1 with a probability between 0 and 1. So we can find a distribution that adds up to 1, therefore state 0 is zero consistent. As concerns state 1, we have something similar, a probability between 0 and 0.5 to loop, and a probability between 0.5 and 1 to go to state 2. So if we take 0.5 in, for example, in both of these intervals, it's add up to 1, and state 1 is zero consistent. Now state 2. State 2 can loop with a probability between 0.3 and 0.4, or we can exit state 2 and go to state 1 with a probability between 0 and 0.5. We can see that here we cannot find any probability distribution that adds up to 1. The maximum here is 0.4, so if I choose the maximum, I will have 0.4, and if I choose the maximum here, 0.5, the sum will be 0.9. So I can never find a combination of these values in these intervals that add up to 1. Therefore, state 2 is not zero consistent. Okay. What is the impact on one consistency of state 1? Well, if state 2 is not zero consistent, then for state 1 to be one consistent, I should not be able to go to state 2. That means that I should choose a probability 0 to go to state 2. However, the probability interval here does not include 0. It starts from 0.5 to 1. So I cannot choose a probability distribution so that I cannot reach state 2 from state 1. Thus, state 1 is not zero consistent. As concerns state 0 allows for reaching itself, and state 1 that was zero consistent, and therefore state 0 is one consistent. Then I repeat that again. What happens for a consistency of state 0? Well, since state 1 is zero consistent but not one consistent, I would like to not to reach state 1 for the consistency of the model. And this is possible because I have 0 in the interval. So I can choose 0 in this interval and say when I'm in state 0, I will not go to state 1. That is not one consistent. To be 2 consistent, my state 0 must be able to have a probability, an exiting probability of 1, which is the case here. So it has a probability of 1 of looping on itself. So at this stage, you have an idea on parametric interval Markov chain. You know how to check consistencies for interval Markov chains. And we'll now see how to check consistency for parametric interval Markov chains in the next sequence.